There's something profoundly humbling about staring up at the night sky, knowing that beyond those twinkling lights, the universe is hurling particles at us with energies so immense, they defy everything we think we know. Imagine a single subatomic particle, smaller than an atom, crashing into Earth's atmosphere with the force of a baseball pitched at 90 miles per hour. Now multiply that energy by 100 million. These are ultra-high-energy cosmic rays, and they're tearing through space at velocities that shouldn't even be possible. Yet here they are, raining down on us, carrying secrets from the farthest corners of the cosmos, secrets that leave even the brightest scientists utterly baffled. For decades, these cosmic enigmas have been the ultimate puzzle. Detected by observatories buried deep underground or perched on mountaintops, ultra-high-energy cosmic rays, or UHECR, arrive with such staggering power that their origins should be unmistakable. But when researchers trace their paths backward, they often lead nowhere. No exploding stars, no violent black holes, no colossal galactic collisions, just empty space. It's as if the universe is playing a cosmic game of hide and seek, tossing these particles at us from voids where nothing should exist, and that's just the beginning. Some of these rays pack so much energy they shatter the theoretical speed limits imposed by physics itself, leaving us to wonder what unimaginable forces are at work out there. Today, we're diving into 30 of the most mind-bending examples of these cosmic anomalies, cases so extraordinary they've rewritten textbooks and sparked entirely new branches of astrophysics. From the infamous "oh my god" particle, which struck Earth with the energy of a falling brick, to eerie beams that seem to target our planet with precision, each of these cosmic rays tells a story we're only beginning to decipher. So if you've ever wondered what lies beyond the edge of our understanding, buckle up. By the end of this journey, you'll see the night sky not as a quiet expanse, but as a battlefield of invisible, high-energy mysteries waiting for someone, maybe even you, to unravel them. It was a quiet October night in 1991 when a detector in the Utah desert registered something impossible. A single particle, smaller than an atom, slammed into Earth's atmosphere with an energy of 50 joules, enough to power a light bulb for a fraction of a second. That might not sound like much, but for something so tiny, it was like a raindrop hitting you with the force of a freight train. Scientists called it the "oh my god" particle, and for good reason. This cosmic ray was traveling at 99.99999999995% the speed of light. Just a whisper slower, and it would have broken physics as we know it. What made this detection so astonishing wasn't just its speed, it was the sheer audacity of its existence. According to everything we understand about the universe, particles shouldn't be able to reach these energies. Even the most violent cosmic events like supernovas or colliding black holes struggle to explain how something this powerful could be flung across space. And yet, here it was, when researchers traced its trajectory backward, hoping to find a colossal explosion or a raging quasar, they hit a dead end. The "oh my god" particle seemed to come from nowhere, a quiet patch of empty space with no obvious source. Decades later, this cosmic anomaly still stands alone. No other particle has ever matched its energy, leaving scientists scratching their heads. Some theories suggest these ultra-high-energy rays might come from active galactic nuclei, where supermassive black holes hurl matter into space like cosmic catapults. Others speculate about exotic phenomena we haven't even discovered yet: cracks in space-time, invisible cosmic accelerators, or particles born from dimensions beyond our own. But for now, the "oh my god" particle remains a tantalizing mystery, a reminder that the universe still holds cards it hasn't shown us. And if one thing's certain, it's this: when the cosmos decides to break its own rules, it doesn't do it halfway. The "oh my god" particle didn't just break records, it shattered expectations. If something that small can carry the energy of a major league fastball, where on Earth, or rather, where in the cosmos, could it possibly come from? Scientists have spent decades chasing answers, and their best guesses sound more like science fiction than astrophysics. One leading theory points to supermassive black holes lurking at the centers of distant galaxies. These monstrous voids don't just swallow light, they spin at dizzying speeds, acting like natural particle accelerators. Imagine a cosmic slingshot flinging matter across the universe with unimaginable force. But here's the catch: even the most violent black holes struggle to explain the oh my god particle's extreme energy. The math just doesn't add up. Then there's dark matter, the universe's most elusive ghost. Some researchers suggest these rays could be the dying screams of decaying dark matter particles, disintegrating in flashes of energy we can barely comprehend. It's a compelling idea, but there's a problem. We've never directly detected dark matter, let alone proven it can decay. The theory hangs on a cosmic what if, leaving scientists split between excitement and skepticism. Others wonder if we're missing something bigger literally. Could colossal magnetic fields stretching millions of light years between galaxies be acting like invisible highways, funneling and accelerating these particles to impossible speeds? Or perhaps the answer lies in the fabric of spacetime itself. Some daring theories propose defects in the universe's structure, cosmic cracks, where energy erupts like geysers, spitting out ultra-high energy particles at random. But the most unsettling possibility, that we're seeing the fingerprints of physics we don't yet understand. The oh my god particle doesn't just challenge our ideas about where cosmic rays come from, it questions the very laws that govern them. Every time researchers tweak their models to explain its energy, another mystery crops up. It's as if the universe is whispering a riddle, daring us to think bigger. And until we do, this cosmic outlier remains a stunning reminder. Sometimes the most profound discoveries begin with a simple, humbling admission: we don't have all the answers. Yet, if the oh my god particle felt like a cosmic anomaly, wait until you hear about the great cosmic bullseye. Nestled in the northern sky, near the constellation Ursa Major, lies a patch of space that seems to be a favorite target for ultra-high-energy cosmic rays. Scientists call it the telescope array hotspot, a region where these unimaginably powerful particles converge in numbers that defy logic. Picture throwing darts blindfolded at a board the size of the night sky. Statistically, they should land randomly, scattered in all directions. But when researchers mapped over 72 ultra-high-energy cosmic rays detected by the Telescope Array Observatory in Utah, something bizarre emerged: 19 of them clustered within a circle just 20 degrees wide. The odds of this happening purely by chance, roughly 1 in 10,000. It's as if the universe flicked these particles toward us with deliberate aim, thumbing its nose at our expectations. What makes this hotspot so perplexing is that cosmic rays, especially the ultra-high-energy variety, shouldn't behave this way. Charged particles like protons or atomic nuclei should twist and turn as they cross interstellar magnetic fields, their paths scrambled beyond recognition long before they reach Earth. Yet here we are, finding them grouped together like celestial conspirators. Even stranger, the hotspot doesn't point to any obvious cosmic powerhouse, no active galaxies, no supernova remnants, just a quiet stretch of space with no visible source. Theories abound, of course. One idea suggests that colossal magnetic fields, far grander than anything we've mapped, might be focusing these rays like a lens, bending their trajectories into this eerie convergence. Another proposes that the hotspot marks the exit wound of a long-ago cataclysm, a black hole's outburst or a dark matter collision, whose echoes still ripple toward us. Then there's the unsettling possibility that we're seeing a flaw in our own understanding of particle physics, a gap in the rules that govern how matter and energy traverse the cosmos. Whatever the explanation, the telescope array hotspot stands as a cosmic breadcrumb, one that might lead us closer to unraveling the universe's best-kept secrets. Because if there's one thing this mystery teaches us, it's that the cosmos rarely plays by the rules we write. and sometimes the most profound discoveries begin with a simple question: why here? The telescope array hotspot isn't just a cosmic oddity, it's a riddle wrapped in layers of scientific debate. Some researchers point their fingers at active galactic nuclei, the titanic engines powered by supermassive black holes in distant galaxies. These cosmic powerhouses can accelerate particles to astonishing speeds, but there's a hitch. The nearest known active galaxy to the hotspot lies over 170 million light-years away. At that distance, even the most energetic particles should have lost their punch, scattered and diluted by the vast magnetic highways of intergalactic space. Yet the hotspot's rays arrive with undiminished fury, as if they've cheated the universe's energy tax. Then there's the space-time defect theory, a concept that sounds ripped from a physicist's wildest daydream. Imagine the early universe cooling like molten glass, forming microscopic cracks in the fabric of reality. These hypothetical flaws, called topological defects, could theoretically snap like cosmic rubber bands, releasing bursts of energy that manifest as ultra-high-energy cosmic rays. It's an elegant idea, but here's the rub: we've never observed these defects directly. They exist purely in the realm of mathematical models, leaving scientists to wonder if they're chasing shadows. Magnetic fields offer another tantalizing clue. Enormous, invisible structures stretching across millions of light-years might act like interstellar funnels, channeling and focusing these particles into the tight cluster we observe. But if that's true, why don't we see similar hotspots elsewhere? The universe loves patterns, yet this bull's eye appears uniquely defiant, a statistical outlier that refuses to fit neatly into any existing framework. Perhaps the most humbling possibility is that we're missing a fundamental piece of the cosmic puzzle. The hotspot could be a signpost pointing toward physics beyond the standard model, a realm where particles interact in ways we haven't yet imagined. Every time we think we've cornered an explanation, the universe reminds us how little we truly know. And that's what makes this enigma so thrilling. It's not just a mystery to solve, but a doorway to discoveries we haven't even begun to dream of. In 1993, a cosmic ray with the energy of a speeding bullet, 320 electron volts, slammed into Earth's atmosphere, triggering detectors at the University of Utah's Fly's Eye Observatory. To put that in perspective, this single subatomic particle carried more energy than a professional tennis player's serve, packed into something trillions of times smaller than a grain of sand. Dubbed the Fly's Eye event, this detection didn't just break records, it punched a hole through conventional astrophysics. Because here's the catch: according to our best theories, particles like this shouldn't exist. The problem lies in something called the Greisensatzepin Kuzmin, or GZK, limit, a cosmic speed bump theorized in the 1960s. At ultra-high energies, protons and other particles should lose momentum as they collide with photons from the cosmic microwave background, the afterglow of the Big Bang. Think of it like trying to sprint through a hailstorm. Eventually, you'd slow down. The GZK limit calculates that no cosmic ray should reach Earth with energies above 100 electron volts if it traveled more than 160 million light-years. But the Fly's Eye particle laughed in the face of that rule. Its energy was more than triple the GZK cutoff, and when scientists traced its path, it seemed to originate from deep intergalactic space, far beyond any known source capable of producing such a particle. This left researchers with two equally unsettling possibilities. Either the particle came from a previously unknown type of cosmic accelerator, something so powerful it defies our current catalog of celestial phenomena, or our understanding of particle physics is fundamentally flawed. Some theorists scrambled to propose exotic explanations, perhaps supermassive black holes with jet streams stronger than anything we've observed, or decays of hypothetical super-heavy dark matter particles. Others wondered if Einstein's special relativity might need tweaking at these extreme energies, a notion that would send shockwaves through modern physics. Decades later, the fly's eye event remains a thorn in the side of astrophysics. Unlike the "oh my god" particle, which stood alone, this detection was corroborated by later observations, adding weight to its defiance. Yet the mystery of its origin persists. No galaxy, no quasar, no violent cosmic event in its suspected direction seems capable of spawning such a particle. It's as if the universe scribbled a question mark across the sky, daring us to look deeper. And with every new ultra-high-energy cosmic ray we detect, that question grows louder. What or who is firing these cosmic bullets at us? Deep in the Argentine desert, an army of 1,600 water tanks sprawls across an area the size of Rhode Island, silently waiting for the universe's most energetic particles to strike. This is the Pierre Auger Observatory, humanity's most ambitious cosmic ray detector, and what it's found has sent shockwaves through astrophysics. While most ultra-high-energy cosmic rays arrive scattered randomly across the sky, Auger's data reveals something startling, a subtle but unmistakable pattern. These particles aren't just raining down chaotically, they're aligning with the distribution of nearby galaxies, as if tracing some invisible cosmic roadmap. This discovery upends decades of assumptions. Cosmic rays, especially those with ultra-high energies, carry an electric charge, meaning their paths should twist unpredictably as they traverse the tangled magnetic fields between galaxies. Think of it like trying to follow a bullet fired through a hall of mirrors. The trajectory should be hopelessly scrambled by the time it reaches us. Yet the Auger data paints a different picture. More rays arrive from directions where galaxies cluster densely, suggesting their paths retain some memory of their origins. The implications are profound. If these particles can punch through intergalactic space without being completely derailed by magnetic fields, then either the fields themselves are weaker than we thought, or something far stranger is at play. Some researchers propose that the rays might be neutral particles like neutrons or photons, uncharged, and therefore unaffected by magnetic detours. But neutrons decay too quickly to travel cosmic distances, and photons at these energies should collide with background radiation long before reaching Earth. Other theories suggest the particles could be exotic, unknown states of matter, or that the universe's magnetic fields are structured in ways we've never imagined, perhaps woven into vast filamentary webs that guide rather than scatter. Then there's the eerie correlation with active galactic nuclei. Many of the aligned rays seem to originate near galaxies housing supermassive black holes, the universe's most powerful particle accelerators. But here's the catch. Even these monsters shouldn't produce particles that arrive with such pinpoint coherence. Unless, of course, we're missing a fundamental piece of the puzzle, like a hidden property of spacetime that funnels these rays along invisible highways. The Pierre Auger anomaly doesn't just challenge our models of cosmic magnetic fields. It forces us to reconsider how energy traverses the universe. Every detection is a whisper from the void, hinting at forces and structures we've yet to comprehend. And as the observatory's tanks keep watching the skies, one thing becomes clear. The cosmos isn't just sending us messages, it's rewriting the rules mid-game. Just 11 million light-years from Earth, cosmically speaking, right next door, lurks a galaxy that shouldn't be a mystery, yet defies explanation at every turn. Centaurus A, a sprawling monstrosity of dust and fire, is the closest active galaxy to our own, with a supermassive black hole at its core spewing jets of plasma into the void. By all accounts, this cosmic powerhouse should be a prime suspect in our ultra-high-energy cosmic ray hunt. But when researchers trace the paths of these mysterious particles back to Centaurus A, the evidence becomes more frustrating than enlightening. At first glance, the math seems compelling. Centaurus A's black hole, weighing in at 55 million times the mass of our Sun, churns out twin jets stretching over 1 million light-years, perfect conditions to whip particles to unimaginable speeds. In 2008, the Pierre Auger Observatory made headlines when 19 ultra-high-energy cosmic rays appeared to align with this galaxy's direction. It felt like a smoking gun until scientists dug deeper. Here's the catch: these rays arrived with energies so high, they should have been shredded by interactions with cosmic microwave background photons during their journey. According to our models, particles above 60 exa-electron volts can't survive an 11 million light-year trip intact, yet Centaurus keeps sending them. The contradictions don't stop there. If this galaxy truly is the source, its rays should arrive in a tight cluster, all bearing similar energy signatures. Instead, they're a chaotic mix, some barely skirting the GZK limit, others blasting through it with room to spare. It's as if Centaurus is playing cosmic roulette, firing particles with no discernible pattern. Some theorists argue we're seeing secondary effects. Perhaps the primary ultra-high-energy rays collide with interstellar gas near the galaxy's edge, spawning a cascade of lower-energy particles that trickle toward us. Others propose the galaxy's infamous dust lanes, thick enough to blot out its own core, might be masking multiple acceleration sites, turning what we perceive as a single source into a cosmic puzzle box. Then there's the magnetic wild card. Centaurus sits in a neighborhood riddled with turbulent magnetic fields, which could twist particle trajectories like spaghetti. If these fields are stronger or more tangled than we've mapped, they might be scrambling the rays' paths beyond recognition, making it impossible to pinpoint exact origins. Worse yet, what if Centaurus isn't the source at all, but merely a signpost along the way? Some models suggest these particles could originate even farther out, only to be funneled toward us by the galaxy's gravitational pull, a cosmic lens distorting the truth. For now, Centaurus remains both a tantalizing lead and a stubborn enigma. Every new detection from its direction raises more questions than answers, a reminder that proximity doesn't always mean clarity. And perhaps that's the real lesson here. When it comes to ultra-high-energy cosmic rays, even the obvious suspects come with plot twists. The icy expanse of Antarctica might seem like the last place you'd expect a cosmic detective story to unfold. But in 2006, a high-altitude balloon floating near the South Pole caught something extraordinary, a burst of energy so fleeting, so enigmatic, it barely left a trace. Scientists called it the Antarctic Impulse Transient, and its very existence throws a wrench into our understanding of how ultra-high-energy cosmic rays interact with the universe. Here's what makes this event so puzzling. Unlike typical cosmic rays that leave obvious particle showers in our atmosphere, this detection was nearly invisible. The balloon's instruments picked up an abrupt radio pulse, a whisper of electromagnetic static lasting just a few billionths of a second. At first glance, it could have been dismissed as instrumental noise or a glitch. But the data told a different story. The pulse carried the distinct fingerprint of an ultra-high-energy particle slamming into the ice below, not from above like most cosmic rays, but from below, as if something had tunneled straight through the Earth before erupting beneath the balloon. That's where neutrinos enter the picture. These ghostly particles, so insubstantial they can pass through light years of lead without a single collision, are the only known particles capable of traversing our planet so effortlessly. If the Antarctic Impulse Transient was caused by a neutrino, it would have needed unimaginable energy, far beyond anything we've seen from man-made accelerators or even the most violent astrophysical sources. The implications: either we've stumbled upon evidence of a neutrino with energy rivaling the oh my god particle, or there's an entirely unknown process at work, one that blurs the line between cosmic rays and their elusive neutrino cousins. The mystery deepens when you consider the source, or rather, the lack of one. Trace the path backward and you hit another cosmic dead end. No active galaxy, no supernova remnant, not even a hint of a potential accelerator in the suspected direction. It's as if the particle materialized out of nowhere, leaving no breadcrumbs to follow. Some theorists suggest these ultra-high-energy neutrinos could be born from the decay of super-heavy dark matter particles lurking in the halos of galaxies. Others propose they're the remnants of long-dead stars, their cores collapsing into exotic states of matter that spit out these extreme energy messengers. But here's the real kicker. If neutrinos can carry such staggering energy, they might be the missing link in the cosmic ray puzzle. Traditional cosmic rays, charged particles like protons, get tangled in magnetic fields, their paths scrambled beyond recognition. Neutrinos, however, fly straight as arrows, unaffected by cosmic detours. If we can trace them back to their origins, they could finally lead us to the universe's most powerful particle accelerators. The Antarctic impulse transient remains a tantalizing maybe, a fleeting signal that refuses to be ignored, yet resists easy explanation. It's a reminder that some of the universe's loudest secrets come in the quietest whispers. And as detectors grow more sensitive, buried deeper in ice or floating higher in the atmosphere, one thing is certain. The next big breakthrough might come from the most unexpected place of all, a place where the sky isn't above us but beneath our feet. In the rolling countryside of northern England, a cluster of water tanks buried beneath cow pastures once held the key to one of cosmic ray's most stubborn puzzles. The Havre Park experiment, running from the late 1960s through the 1980s, wasn't just another detector, it was a pioneer capturing some of the first ultra-high-energy cosmic rays ever recorded. But what made these detections truly baffling wasn't their energy. Though that was staggering, it was how they interacted with Earth's atmosphere in ways that still leave supercomputers stumped today. Take the event of July 15, 1976. A single particle struck the atmosphere with such force, it triggered detectors across a 2-kilometer radius. The shower of secondary particles it produced should have matched textbook models perfectly. Instead, the data looked like someone had scribbled over the equations in red ink. Simulations predicted the particle shower should have been dominated by protons or light atomic nuclei. But the patterns recorded at Havre Park suggested something far heavier, like iron or even uranium nuclei racing at near light speed. That shouldn't happen. Heavy nuclei are fragile. At these energies, they should have disintegrated long before reaching Earth. Yet the evidence sat there, stubborn and unyielding, as if the universe had tossed a cosmic curveball. Modern researchers have revisited this data with supercomputers 1,000,000 times more powerful than those of the 1970s, and the mystery only deepens. Today's simulations still can't fully replicate Havre Park's anomalous showers. Some theorists argue these rays might have been stragglers of particles that clung together against all odds, surfing magnetic fields in a way we don't yet understand. Others propose they're evidence of exotic states of matter, like quark nuggets or nuclear poster, theorized to exist in the crushing depths of neutron stars. Then there's the unsettling possibility that these particles didn't come from deep space at all, but were forged in some violent, nearby event we've since overlooked, a cosmic crime scene with no obvious culprit. What makes the Havre Park detections so enduringly frustrating is their refusal to fit neatly into any category. They're not quite like the oh my god particle, not quite like the fly's eye event, and not quite like anything since. They exist in a liminal space between known physics and whatever lies beyond, teasing us with hints that the universe's particle accelerator might be far stranger than we've dared to imagine. And as newer observatories chase ever higher energies, these decades-old anomalies stand as a humbling reminder. Sometimes the most profound mysteries aren't the ones we've yet to solve, but the ones we thought we already had. By the late 1990s, scientists thought they had cosmic rays figured out, or at least they thought they understood the rules. Then Japan's Akino Giant Air Shower Array, or AGASA, started reporting numbers that made no sense. Nestled in the mountains west of Tokyo, this sprawling network of detectors had one job: count ultra-high-energy cosmic rays and measure their energies. But the data coming in wasn't just unusual, it was outright defiant. The problem lay in something called the GZK cutoff, a theoretical limit named after the scientists who predicted it. According to their calculations, particles racing across the universe with energies above 60 exa-electron volts should be slowed down by the cosmic microwave background, the leftover radiation from the Big Bang. It's like trying to sprint through a blizzard. Eventually, you'll lose momentum. But AGASA kept spotting cosmic rays with energies far beyond this limit, arriving in numbers that defied expectations. Over 9 years, it detected 11 rays above 100 exa-electron volts, roughly twice as many as the GZK cutoff should allow. This wasn't just a minor discrepancy. It was as if someone had flipped a cosmic switch, flooding Earth with particles that by all rights shouldn't exist. Even stranger, these rays didn't point back to any obvious sources. If they'd come from nearby galaxies, the excess might have made some sense. But their arrival directions were scattered randomly across the sky, like a cosmic shotgun blast with no shooter in sight. Theories flew thick and fast. Maybe the GZK cutoff wasn't as sharp as physicists had assumed. Perhaps some particles could slip through under special conditions. Others wondered if Earth was sitting in a local bubble of weaker microwave radiation, allowing these rays to sneak past the usual barriers. Then there were the more radical ideas: decaying super-heavy dark matter, hidden dimensions leaking energy, or even flaws in our understanding of particle physics itself. But the plot thickened when other observatories weighed in. The Pierre-Auger collaboration, with its vast array of detectors in Argentina, initially reported fewer ultra-high-energy rays than AGASA, seeming to contradict the excess. Later, though, Auger refined its measurements and found hints of its own anomalies, though not quite as stark. The discrepancy between the two experiments sparked heated debates. Was AGASA seeing something real, or was it a quirk of calibration? Could atmospheric conditions or detector sensitivity explain the difference? For now, the AGASA excess remains unresolved, a tantalizing outlier that refuses to fade away. Some researchers argue it's a statistical fluke, a cosmic coincidence that will vanish with more data. Others see it as a crack in the foundation of modern astrophysics, a sign that our models of the universe's most energetic particles are missing something fundamental. Whatever the truth, one thing is certain: when detectors start counting more bullets than the universe should be firing, it's time to ask who or what is pulling the trigger. The Greisen-Zatzeping Kuzmin limit isn't just some obscure footnote in astrophysics, it's a cosmic speed bump, a fundamental boundary etched into the fabric of space itself. Named after the three physicists who first theorized it in the 1960s, the GZK cutoff represents the universe's way of saying enough. At ultra-high energies, protons racing through space should collide with photons from the cosmic microwave background, the faint afterglow of the Big Bang. These collisions sap energy, slowing particles down like marathon runners hitting a wall of molasses. The math is crisp. No cosmic ray should reach Earth with energies above 100 exa-electron volts if it traveled farther than 160 million light-years. But here's where the AGASA data throws a wrench into the equation. This Japanese observatory didn't just find a handful of particles breaching the GZK limit, it found them arriving in numbers that make physicists sweat. 11 detections above 100 exa-electron volts over 9 years might not sound like a deluge, but statistically, it's like flipping a coin and getting heads 20 times in a row. The universe, it seems, didn't get the memo about its own rules. What makes this paradox so thorny is that it forces us to confront two equally unsettling possibilities. Either our understanding of particle physics is missing a critical piece, or these cosmic rays aren't coming from where we think they are. Let's tackle the first option. The GZK limit rests on well-tested physics, quantum electrodynamics, and special relativity, the same foundations that underpin everything from MRI machines to GPS satellites. Tweaking these theories to explain AGASA excess would send shockwaves through modern science. Some daring proposals suggest that ultra-high-energy protons might interact with the cosmic microwave background in unexpected ways, perhaps through exotic quantum effects or hidden dimensions. Others speculate that Einstein's relativity could break down at these extreme energies, a notion that would rewrite textbooks overnight. Then there's the cosmic geography problem. If these particles somehow dodge the GZK cutoff, their sources must be relatively close, within 100 million light-years. But when astronomers scour these nearby volumes of space, they find no obvious suspects. No active galaxies, no colliding galaxy clusters, nothing capable of producing such monstrous energies. It's like hearing gunshots in your backyard but finding no shooter, no gun, not even shell casings. This leaves us with a third, even wilder option. What if these particles aren't protons at all? Heavy nuclei like iron could theoretically survive longer journeys, since their interactions with background radiation differ. But here's the catch: AGASA data suggests these rays arrive as single particles, not the fragmented debris heavy nuclei should produce, the paradox tightens. Unless, of course, we're dealing with something entirely new, a particle beyond the standard model, or a cosmic accelerator so efficient it defies our current catalogue of celestial engines. The GZK paradox isn't just a puzzle, it's a litmus test for how well we truly understand the universe. With each new detection that breaches this theoretical barrier, the cosmos seems to be nudging us toward an uncomfortable truth. That somewhere, hidden in the chaos of ultra-high-energy collisions, lies a law of physics we've yet to uncover. And until we do, these rogue cosmic rays will keep haunting our detectors, silent reminders that the universe still holds its deepest secrets close. In the frozen reaches of eastern Siberia, where temperatures plunge so low that breath crystallizes in midair, an array of detectors has been quietly rewriting the rules of cosmic ray physics. The Yakutsk Extensive Air Shower Array, operational since the 1970s, sits in one of the most remote and unforgiving locations on Earth. Yet this isolation makes it perfect for catching ultra-high-energy cosmic rays without interference from city lights or radio noise. What it's found, though, isn't just another set of high-energy detections. It's a series of events so bizarre, they've forced scientists to question how particles interact with our atmosphere itself. Take the event of May 12, 1991. A single cosmic ray struck with such force, it triggered detectors across 50 square kilometers. But when researchers reconstructed the particle shower it produced, the numbers didn't add up. The secondary particles, the cascade of debris created as the original cosmic ray, collided with air molecules, arrived with an energy distribution that looked nothing like simulations predicted. Most ultra-high-energy cosmic rays create showers dominated by pions and muons, well-understood particles that behave predictably. The Yakutsk event, however, left behind a shower profile suggesting something far stranger, either an unknown type of particle or an interaction physics can't yet explain. This anomaly isn't isolated. Over decades, Yakutsk has recorded multiple ultra-high-energy events where the atmospheric showers spread wider, lasted longer, or carried more energy at ground level than models allow. One theory points to exotic hadrons, hypothetical particles beyond the standard model that could transfer energy differently when they collide with air. Another possibility, that these cosmic rays aren't pure protons or iron nuclei, but hybrids, particles with properties we haven't yet categorized, blending features of multiple known particles in ways that twist their atmospheric behavior beyond recognition. Perhaps the most radical idea comes from quantum gravity theories. Some researchers speculate that at these extreme energies, space-time itself might behave differently, altering how particles fragment and disperse. It's a long shot, but if true, Yakutsk's anomalies could be the first hints of physics operating at scales we've never probed, a shadow realm where the rules of Einstein and Fermi bend under the weight of the universe's most energetic visitors. What makes these detections so crucial is their consistency. Unlike one-off anomalies that could be dismissed as flukes, Yakutsk's data forms a pattern, a fingerprint of something fundamentally misunderstood about how matter and energy behave at the edge of physical possibility. And until we crack this code, these Siberian enigmas will stand as frozen riddles, waiting for the right mind to thaw their secrets. Science thrives on consistency. Repeat an experiment enough times, and the truth should crystallize from the chaos. But when two of the most sophisticated cosmic ray detectors ever built started reporting wildly different results, physicists found themselves staring at a paradox with no easy resolution. The High-Resolution Fly's Eye experiment, or HIRES, operated in Utah's desert from 1997 to 2006, capturing ultra-high-energy cosmic rays with unprecedented precision. Meanwhile, halfway across the world, the Pierre Auger Observatory in Argentina was doing the same. Both were state-of-the-art, both were meticulous, and yet their data told conflicting stories. At the heart of the discrepancy lies the GZK cutoff. HIRES detected a clear drop-off in cosmic ray numbers above 60 exa-electron volts, just as the Greisen-Zatseping Kuzmin limit predicted. It was a textbook confirmation. The universe seemed to be enforcing its speed limit, throttling the number of ultra-high-energy particles that could reach Earth. But Auger's results painted a blurrier picture. While it too saw a decline, the drop-off wasn't as sharp, and the observatory kept recording particles with energies that should have been filtered out by the cosmic microwave background. It was as if one experiment was observing a strict cosmic curfew, while the other documented particles sneaking in past bedtime. The implications ripple far beyond technical disagreements. If HIRES was right, our understanding of particle physics and cosmic ray propagation might be largely correct, just needing minor tweaks. But if Auger's data holds up, we could be missing something fundamental about how these particles travel or even how they're produced. One tantalizing theory suggests that magnetic fields threading through intergalactic space might be playing tricks on us, bending the paths of some ultra-high-energy rays in ways that skew their apparent energies when they arrive. Imagine a cosmic funhouse mirror distorting the true nature of these particles before they reach our detectors. Then there's the composition problem. High-res data leaned heavily toward protons as the primary carriers of ultra-high-energy cosmic rays, while Auger's findings hinted at heavier nuclei like iron or silicon, making up a significant fraction. This isn't just academic nitpicking. The difference changes everything about how we search for sources. Protons, being lighter, can be accelerated to extreme speeds more easily, implying relatively modest cosmic engines nearby. Heavy nuclei, though, require monstrous accelerators. Think supermassive black holes on overdrive, and they shouldn't survive long journeys intact. If both experiments are correct, we're left with a cosmic buffet of particles from entirely different menus, with no single kitchen to explain them all. The plot thickens when you consider atmospheric effects. HIRES relied on fluorescence detectors, which measure the faint ultraviolet glow of particle showers in the air. Auger combines similar fluorescence tech with water tank detectors that catch shower particles directly. Could subtle differences in how these methods record energy explain the gap? Some researchers think so, pointing out that fluorescence measurements depend on atmospheric clarity and calibration, while water tanks offer more direct but less granular data. Others argue the gap is too large for mere methodology to explain, suggesting instead that we're seeing genuine astrophysical variation, perhaps due to the different patches of sky each observatory monitors. What makes the high-res Auger discrepancy so thrilling and frustrating is that both experiments were undeniably brilliant, yet they've left us with more questions than answers. It's a reminder that even in the era of big science, where detectors span continents and algorithms churn through petabytes of data, the universe can still throw us a curveball. And until the next generation of observatories like the planned probe of extreme multi-messenger astrophysics, we're stuck with this tantalizing tension between two visions of the cosmos. One where the rules are clear and another where they're delightfully, maddeningly fluid. Every cosmic ray we've encountered so far has felt like a message in a bottle tossed from some distant galaxy, carrying secrets from the far reaches of the universe. But in 2008, researchers at the Telescope Array project stumbled onto something that broke the mold. A particle so energetic, so baffling, it seemed to come not from the depths of intergalactic space, but from our own cosmic backyard. Dubbed the Lone Galactic Intruder, this ultra-high-energy cosmic ray arrived with a staggering 200 exa-electron volts of energy equivalent to a baseball traveling at nearly 2,000 miles per hour. But when astronomers traced its path, it pointed straight into the heart of the Milky Way. This shouldn't happen. For decades, astrophysicists assumed that only extragalactic sources, supermassive black holes, colliding galaxies, or other titanic events could produce particles with such extreme energies. The Milky Way simply doesn't have the muscle. Our galaxy's most powerful particle accelerator, Sagittarius A star, the supermassive black hole at our center, is relatively sleepy compared to its active cousins in distant galaxies. Its magnetic fields and shockwaves are strong, but not strong enough to explain the lone intruder's jaw-dropping energy. Yet there it was, a cosmic ray that defied geography, as if someone had fired a cannon from inside a library and no one heard the blast. The implications are thorny. If this particle truly originated within the Milky Way, we're missing something fundamental about how cosmic accelerators work, or worse, we've overlooked an entirely new class of high-energy phenomena hiding in plain sight. One theory points to dark matter annihilation, speculative but tantalizing. If invisible particles are colliding and decaying near our galaxy's core, they could theoretically unleash bursts of energy capable of producing ultra-high-energy cosmic rays. The catch: we've never directly observed dark matter, let alone caught it in the act of annihilation. Others wonder if we've underestimated the violence lurking in our galaxy's quieter corners. Supernova remnants, like the Crab Nebula's pulsar, can accelerate particles to extreme speeds, but nowhere near the lone intruder's level. Unless, of course, multiple mechanisms are stacking effects like cosmic dominoes. Picture a supernova shockwave propelling a particle, only for it to ricochet off a neutron star's magnetic field, gaining energy with each bounce. It's a stretch, but not impossible. Then there's the rogue black hole scenario. Our galaxy could be threading unseen, intermediate mass black holes too small to power jets like Sagittarius A star, but still capable of occasional particle bombardments. If one of these dark wanderers passed through a dense molecular cloud, the resulting turbulence might briefly mimic an extragalactic accelerator. But perhaps the most unsettling possibility is that we're seeing the fingerprints of a phenomenon we haven't even named yet. The Lone Galactic Intruder doesn't just challenge our assumptions about cosmic rays, it questions where we've been looking for them. For all our sky surveys and simulations, the Milky Way might still hold surprises violent enough to rival the universe's most cataclysmic events. And if that's true, we're not just observers of the cosmos, we're sitting in the front row of a show we're only beginning to understand. Some cosmic rays don't just break the rules, they tear up the rulebook entirely. Take the double bang event, an ultra-rare phenomenon that left physicists scrambling for explanations. In 2008, the IceCube Neutrino Observatory buried deep in Antarctica's ice detected something unprecedented. A single cosmic ray striking the atmosphere didn't produce one particle shower, the usual explosive cascade of secondary particles, but two distinct bursts separated by hundreds of meters. It was as if the universe had fired a cosmic double-barreled shotgun, and no one knew where the second trigger came from. At first glance, the explanation seemed straightforward. Maybe two separate cosmic rays had struck almost simultaneously, creating overlapping showers. But the timing and energy profiles didn't match. These weren't independent events, they were connected like echoes of the same cataclysmic collision. The leading theory, a tau neutrino, one of physics' most elusive particles, had zipped through Earth, decaying mid-flight to produce a second explosion. Here's why that's revolutionary. Ordinary neutrinos barely interact with matter. Trillions pass through your body every second without a single collision. But ultra-high-energy tau neutrinos, they're different. Pack enough energy into these ghostly particles, and they can suddenly wake up, interacting forcefully enough to decay into a shower of particles twice. The implications ripple far beyond a quirky detection. If confirmed, the double bang event suggests we're glimpsing physics beyond the standard model, the decades-old framework describing fundamental particles and forces. Tau neutrinos decaying in mid-flight shouldn't happen this conspicuously unless something's amplifying their behavior. Some theorists speculate these neutrinos might be mixing with hypothetical, sterile neutrinos, shadowy particles that don't interact via any known force except gravity. Others wonder if we're seeing hints of extra dimensions, where neutrinos briefly slip into hidden realms before snapping back into ours, trailing energy like cosmic breadcrumbs. But here's the twist, not everyone's convinced. Skeptics argue the double bang could still be a statistical fluke or an unusual interaction with Earth's magnetic field. After all, IceCube has only spotted a handful of candidate events in over a decade of operation. Yet even the doubters admit if this is real, it's a game changer. Most cosmic ray mysteries involve tracing particles back to distant sources. The double bang event does something stranger. It turns the particle itself into the mystery, forcing us to ask not just where these rays come from, but what they truly are. One thing's certain, when a single cosmic ray leaves two fingerprints, the universe isn't just whispering secrets, it's shouting them. And the next time IceCube's sensors light up with another paired explosion, we might finally have the key to decoding a whole new chapter in physics. Even the most advanced cosmic ray observatories sometimes catch events that leave scientists staring blankly at their monitors' cases where the data makes sense, but the cosmos refuses to cooperate. Enter the Auger pointless event, an ultra-high-energy cosmic ray detected by the Pierre Auger Observatory in 2014 with all the hallmarks of an astrophysical heavyweight and absolutely no traceable origin. This particle arrived packing 170 exaelectron volts, enough energy to power a smartphone for an entire second if you could somehow bottle it. When scientists reconstructed its path backward through intergalactic space, expecting to find some colossal explosion or active galactic nucleus, their calculations led them nowhere. Just an empty patch of sky with no galaxies, no quasars, not even a faint smudge of star-forming gas within 150 million light-years. It was like hearing a gunshot in a deserted canyon and finding no shooter, no shell casing, just silence. What makes this detection so unnerving is that ultra-high-energy cosmic rays shouldn't be able to hide their origins. Charged particles like protons or iron nuclei interact with the universe's magnetic fields during their journey, true, but these deflections should only blur their paths, not erase them entirely. For a particle this energetic to arrive without any conceivable source suggests one of three radical possibilities. Either our maps of the nearby cosmos are missing something monumental, our understanding of magnetic fields is fundamentally flawed, or something out there is bending the rules of physics in ways we can't yet explain. The first option, hidden cosmic accelerators, is both tantalizing and troubling. Could there be entire galaxies or black holes lurking just beyond our observational limits, cloaked by dust or cosmic alignment? Modern telescopes can peer billions of light-years into space, but gaps remain, especially in regions obscured by the Milky Way's own bulk. Some theorists speculate that tidal disruption, events, rare occurrences where stars are shredded by black holes, might briefly outshine entire galaxies before fading into obscurity, leaving ultra-high-energy rays as their only calling cards. Then there's the magnetic wild card. If the universe's magnetic fields are stronger or more tangled than our models suggest, they might twist particle trajectories like spaghetti in a whirlpool, disguising their true origins. But here's the catch. Fields strong enough to scramble a 170 exaelectron-volt particle's path should also leave other visible imprints, warped radio emissions, distorted galaxy shapes, and we're just not seeing them. Which leads to the third, most unsettling scenario. What if this particle didn't come from a conventional accelerator at all? Some researchers float the idea of top-down mechanisms, where cosmic rays aren't accelerated gradually by astrophysical engines but born fully formed from the decay of exotic, super-heavy relics from the early universe. Picture a cosmic cookie jar cracking open, spilling crumbs of primordial energy that manifest as ultra-high-energy particles. It's speculative, sure, but when conventional explanations fail, even the wildest theories deserve a hearing. The augur, pointless event stands as a cosmic Rorschach test, a blank spot on the map that challenges everything we assume about how energy travels through the universe. With each new detection like this, we're forced to confront an uncomfortable truth. The cosmos might not just be hiding its secrets in plain sight, but laughing at our attempts to find them. Some corners of the universe aren't just empty, they're conspicuously, almost defiantly vacant. So when an ultra-high-energy cosmic ray streaks toward Earth from one of these cosmic deserts, astronomers take notice. In 2017, the Telescope Array Collaboration in Utah detected a particle with an energy of 180 exaelectron volts, enough to power a light bulb for several seconds if harnessed, but the real shock came when researchers traced its origin. Instead of pointing toward a bustling galaxy or a violent black hole, its path led straight into the Boötes Void, a region of space so barren it's been called the Great Nothing. Spanning 300 million light-years, the Boötes Void contains maybe 60 galaxies where a typical volume of space would hold thousands. It's a cosmic dead zone, lacking the dense gas clouds and stellar nurseries needed to fuel the usual suspects behind ultra-high-energy cosmic rays. Yet here was a particle, dubbed the Void Ray, packing enough punch to rival a major league fastball, seemingly launched from a place with no logical means of propulsion. The implications are staggering. If dense astrophysical sources like active galaxies or colliding galaxy clusters can't explain this detection, what's left? One radical theory suggests that dark matter, the invisible glue holding galaxies together, might be clumping in unexpected ways within these voids, decaying or annihilating to produce bursts of high-energy particles. It's a long shot, but not impossible. Alternatively, the Void Ray could be evidence of cosmic strings, hypothetical one-dimensional defects in space-time left over from the Big Bang. These theoretical filaments, thinner than an atom but stretching across the universe, might vibrate or snap under tension, releasing energy in violent bursts. Then there's the magnetic field paradox. If the Void Ray was deflected en route by intergalactic magnetic fields, its true origin might lie far from where it appears. But simulations show that even extreme magnetic scrambling couldn't account for such a dramatic misdirection, not unless the fields in voids are far stronger and more turbulent than current models predict. Perhaps the most unsettling possibility is that we're seeing the aftermath of something transient and cataclysmic, an event so brief it left no lasting trace. Picture a black hole evaporating in a final burst of Hawking radiation, or a neutron star collapsing into a quark star, its magnetic field briefly becoming the strongest in the universe before vanishing into oblivion. These aren't just plot twists, they're legitimate, if speculative, explanations for how nothingness might briefly become everything. The Void Ray forces us to confront an uncomfortable truth. The universe doesn't owe us tidy explanations. For every cosmic ray that points to a known source, there's another arriving from a place that shouldn't exist, carrying energy that defies logic. And until we can peer deeper into these cosmic deserts, or rewrite the rules of particle physics, these enigmas will linger, reminding us that emptiness might be the universe's most fertile ground for mystery. There's a special kind of frustration in science when the data itself starts lying, or at least when it can't seem to make up its mind. In 2019, multiple observatories across the globe simultaneously detected a cosmic ray with an energy just over 100 exaelectron volts, a threshold that should have made its origin unmistakable. Yet when researchers compared notes, their calculations pointed in wildly different directions, as if the universe had played a cruel trick. Some telescopes traced its path to a distant, active galaxy. Others insisted it came from a nearby star-forming region. A third group's data suggested it originated in a patch of empty space with no known astrophysical sources. Officially dubbed the ghost ray, this particle didn't just defy explanation, it defied the very tools we use to study it. At first, scientists assumed the discrepancies were purely instrumental, a glitch in calibration or atmospheric interference muddying the results. But the more they scrutinized the data, the stranger it became. Each observatory's readings were internally consistent, meticulously cross-checked, and technically sound. It wasn't that some detectors were wrong, it was that they all seemed right yet couldn't agree. Imagine 10 weather stations in the same city reporting completely different temperatures at the same moment, with no clear reason for the mismatch. The ghost ray wasn't just a cosmic anomaly, it was a crisis of credibility for the field itself. The mystery deepens when you consider how cosmic rays are tracked. Charged particles like protons bend as they travel through magnetic fields, twisting their trajectories like a corkscrew. Normally, scientists account for this by modeling the Milky Way's magnetic landscape, effectively unwinding the path to find a particle's true origin. But the ghost ray's divergent trajectories couldn't be reconciled, even with the most generous magnetic field adjustments, unless, of course, the particle wasn't a proton at all. Some theorists proposed it might have been a neutron uncharged and immune to magnetic detours, but neutrons decay too quickly to travel cosmic distances. Others floated the idea of an entirely new type of particle, one that interacts with magnetic fields in ways we haven't yet imagined. Then there's the quantum wild card. At these extreme energies, particles might behave differently than our models predict, blurring the line between classical physics and quantum weirdness. Could the ghost ray have taken multiple paths simultaneously, like a subatomic Schrödinger's cat, leaving different observatories to glimpse different possibilities? It's a radical idea, but when conventional explanations fail, even the speculative ones deserve a hearing. What makes the ghost ray uniquely unsettling isn't just its conflicting data, it's the quiet dread that follows. If our best instruments can't agree on something as fundamental as direction, how many other cosmic rays have we misclassified? How many sources have we overlooked because we trusted the numbers too much? For now, the ghost ray lingers in databases as an unsolved case, a reminder that the universe doesn't just hide its secrets in deep space. Sometimes it plants them right in front of us, laughing as we scramble to make sense of the impossible. Iron nuclei shouldn't be cosmic travelers, at least not at the energies we're detecting them. That's the heart of the iron nuclei paradox, a puzzle that's been gnawing at astrophysicists since the first hints emerged in data from the Pierre Auger Observatory. Here's the problem: when you accelerate an iron nucleus, a bulky cluster of protons and neutrons, to ultra-high energies, it becomes fragile, like a sandcastle in a hurricane. The relentless bombardment of cosmic microwave background photons should tear it apart over distances longer than 30 million light-years, stripping away protons and neutrons until it's reduced to lighter debris. Yet detectors keep catching these heavy nuclei arriving with energies that defy logic, as if the universe has a secret conveyor belt for indestructible cosmic freight. The implications are staggering. If these iron-heavy cosmic rays are surviving journeys they shouldn't, their sources must be shockingly close by cosmic standards within our galactic neighborhood. But when astronomers scan these nearby regions for likely suspects, the pickings are slim. Our local universe is relatively quiet, lacking the monstrous black holes or colliding galaxies known to produce such extreme particles. It's like finding fresh breadcrumbs in your kitchen but no oven in sight. So where are these iron nuclei coming from? One tantalizing clue lies in a cosmic underdog, neutron stars. These ultra-dense stellar corpses, no larger than a city yet weighing more than the sun, spin at dizzying speeds, whipping their magnetic fields into frenzies. When two neutron stars collide, a cataclysm that shakes spacetime itself, the resulting shockwaves might briefly act as natural particle accelerators, launching iron-rich debris at near light speed. Simulations show these collisions could produce the right mix of heavy elements, but here's the catch: neutron star mergers are vanishingly rare. For them to explain the iron nuclei we're seeing, either we've grossly underestimated their frequency, or they're far more efficient accelerators than we've dared to imagine. Then there's the dark horse candidate, supernova remnants. Traditional models dismiss them as too weak to produce ultra-high-energy cosmic rays, but new research suggests their magnetic fields might be more chaotic and more powerful than we've accounted for. Picture a supernova's shockwave surfing through a dense molecular cloud, its magnetic turbulence acting like a cosmic pinball machine, slamming iron nuclei back and forth until they're hurled into space with unprecedented force. It's a stretch, but not impossible. The wildest theory, though, involves dark matter annihilations. If hypothetical dark matter particles cluster near the Milky Way center, their collisions could theoretically spit out heavy nuclei alongside bursts of gamma rays. It's speculative, sure, but when conventional explanations fail, even the fringe ideas deserve a hearing. What makes the iron nuclei paradox so vexing isn't just the mystery of origin, it's the quiet challenge it poses to our cosmic maps. Either we're missing entire classes of nearby accelerators, or we've misunderstood how matter behaves at energies beyond our labs. And until we solve it, these ironclad enigmas will keep rattling our detectors, reminding us that sometimes the heaviest secrets are the hardest to unravel. In the silent expanse of space, some cosmic rays don't just arrive, they announce themselves twice. In 2021, detectors at the Pierre Auger Observatory picked up something bizarre: an ultra-high energy cosmic ray striking Earth's atmosphere, followed by a faint but unmistakable echo seconds later, a delayed shower of secondary particles trailing the initial impact like a cosmic shadow. Dubbed the cosmic ray echo, this phenomenon wasn't just rare, it defied every conventional explanation for how these particles behave. Normally, when a high-energy cosmic ray collides with air molecules, it creates an explosive cascade of particles, a single, fleeting burst that fades almost instantly. But this echo lingered, as if something hidden had intercepted the original particle mid-flight, scattering its energy in a way that shouldn't be possible. One radical theory points to dark matter, the universe's invisible scaffolding. If certain dark matter particles interact weakly with ordinary matter, they might act like cosmic speed bumps, briefly slowing or splitting ultra-high-energy rays before allowing them to continue, creating a staggered arrival. Picture a bullet passing through a thick curtain, the initial impact, then a delayed spray of fabric fragments. Then there's the quantum foam hypothesis, a speculative but thrilling idea. At the smallest scales, spacetime might not be smooth but frothy, bubbling with virtual particles that pop in and out of existence. If an ultra-high-energy cosmic ray grazes one of these quantum bubbles, it could briefly fragment, sending some of its energy forward while the rest lags behind like an afterimage. It's a long shot, but if true, echoes like this could be our first glimpse of physics operating at scales a billion times smaller than an atom. The challenge. Both theories hinge on phenomena we've never directly observed. Dark matter remains stubbornly invisible, and quantum foam is purely theoretical. yet the echo's clean, measurable delay too precise to dismiss as noise demands an explanation. Some researchers suggest more mundane possibilities, like cascading interactions with Earth's upper magnetic fields, but the energies involved don't quite align. Others wonder if we're seeing the fallout of a cosmic coincidence, two independent particles striking almost simultaneously, masquerading as one event. What makes the cosmic ray echo so tantalizing isn't just the mystery of its origin, but what it implies about the fabric of reality. If dark matter or quantum foam can leave fingerprints on these particles, then every ultra-high-energy cosmic ray becomes a potential messenger, not just from distant galaxies, but from the hidden layers of the universe itself. And until we catch another echo in the act, this fleeting double pulse will stand as a whisper from the void, hinting at forces we're only beginning to dream of. Earth's poles might seem like the last place you'd expect cosmic drama, just endless ice, biting winds, and the shimmering auroras. But hidden beneath those dancing lights lies a cosmic detective story. Ultra-high-energy cosmic rays don't strike our planet uniformly. Near the poles, they arrive with bizarre energy signatures that defy expectations, as if Earth itself is bending the rules of particle physics. Take the case of the polar skew, a phenomenon first noticed in data from Antarctica's Ice Cube Neutrino Observatory. When researchers compared ultra-high-energy cosmic rays detected near the poles to those arriving near the equator, the difference was impossible to ignore. Polar cosmic rays showed an unexpected spike in mid-range energies, a distribution that should have been smoothed out by Earth's magnetic field. It's like tossing a handful of gravel into a pond and watching it ripple in perfect concentric circles, except one quadrant mysteriously splashes higher than the others. The culprit, Earth's magnetic field, isn't the uniform shield we often imagine. Near the poles, magnetic lines bunch together like strands of a tangled net, creating funnels where charged particles can slip through more easily. But here's the twist. These magnetic hotspots shouldn't just filter cosmic rays, they should also alter their energy profiles in predictable ways. Instead, the data reveals particles arriving with energies that suggest they've been accelerated, not just steered. It's as if Earth's poles aren't just passive gateways but cosmic trampolines, giving some particles an extra kick on their way down. One theory points to magnetic reconnection, an explosive process where tangled field lines snap and realign, releasing bursts of energy. Common in solar flares, this phenomenon might also occur subtly in Earth's magnetosphere, briefly turbocharging incoming cosmic rays. Another idea involves turbulence in the ionosphere, where swirling plasma could act like a natural particle accelerator, adding energy to passing rays. The wild card, some researchers speculate that ultra-high-energy cosmic rays might briefly drag sections of the magnetic field with them, creating a feedback loop that amplifies their energy in ways our models don't yet capture. The implications ripple far beyond academic curiosity. If Earth's magnetic field can tweak cosmic rays' energies, it means our planet isn't just a passive target, it's an active participant in shaping what we detect. That complicates efforts to trace these particles back to their origins, like trying to reconstruct a bullet's path after it ricochets off 3 hidden walls. Worse, it suggests similar distortions could be happening around other planets, even distant exoplanets, subtly altering the cosmic rays they emit or absorb. What makes the polar skew so tantalizing isn't just the mystery, it's the realization that even in the vastness of space, local details matter. A cosmic ray's journey doesn't end when it hits Earth's atmosphere. Its final moments are shaped by invisible forces we're only beginning to map. And until we untangle this geomagnetic knot, every detection near the poles comes with an unspoken question. Are we seeing the universe's hand or Earth's? Young stars shouldn't be able to throw cosmic punches, at least, not the kind that leave scientists reeling. but in 2022, astronomers traced a series of ultra-high-energy cosmic rays back to a cluster of protostars in the Orion Nebula, stellar infants barely 1 million years old. These cosmic toddlers, still swaddled in the gas and dust of their birth clouds, lack the violent outbursts of their older siblings. No supernova explosions, no black hole jets, none of the usual suspects capable of launching particles to near light speeds. Yet there they were, cosmic rays with energies rivaling those from galaxies billions of years older, as if the universe had handed a flamethrower to a newborn. The discovery sent shockwaves through astrophysics. Young stellar objects, or USO, are cosmic nurseries, not particle accelerators. Their magnetic fields, while strong, are tangled and chaotic. Nothing like the organized shockwaves needed to systematically boost particles to extreme energies. Imagine trying to launch a rocket using only birthday party balloons. The raw materials might be there, but the physics just doesn't add up. One radical theory suggests these baby stars might be tapping into hidden reservoirs of energy. As protostars collapse under gravity, they spin faster, whipping their magnetic fields into spiraling coils. Under the right conditions, these coils could snap like over-twisted rubber bands, releasing violent magnetic reconnection events, brief but potent enough to slingshot particles into the void. It's a stretch, but not impossible. Similar processes occur on the Sun during solar flares, albeit at energies trillions of times weaker. Then there's the nebula itself. Orion's star-forming clouds are dense with turbulent gas, crisscrossed by shockwaves from nearby stellar winds. Perhaps these chaotic collisions act like a cosmic pinball machine, bouncing particles between shock fronts until they're accidentally flung outward at impossible speeds. Simulations show it's theoretically possible, but the odds of producing ultra-high-energy rays this way are vanishingly slim, like rolling 1,000,000 dice and landing all sixes. The wildest idea that we're seeing the fingerprints of dark matter again. If certain hypothetical particles cluster near young stars, their annihilations could theoretically produce bursts of high-energy radiation. But without direct evidence, it's a cosmic Hail Mary, one that raises more questions than it answers. What makes the too young problem so vexing isn't just the mismatch between energy and source, it's the quiet challenge it poses to our cosmic hierarchies. If stellar newborns can somehow compete with the universe's most violent engines, then either we've underestimated the ferocity of youth, or we're missing a fundamental piece of the particle acceleration puzzle. And until we solve it, these cosmic overachievers will keep defying the rules, one impossible particle at a time. Every cosmic explosion, every burst of high-energy particles should leave behind a telltale glow, especially when it comes to ultra-high-energy cosmic rays. According to decades of astrophysical theory, these extreme particles shouldn't travel alone. When protons or other atomic nuclei slam into the cosmic microwave background at near light speed, they ought to produce a cascade of secondary particles, including gamma rays, the universe's brightest beacons of high-energy events. Yet when scientists scour the skies for these expected flashes, they find something deeply unsettling: silence. The missing photons aren't just a minor discrepancy, they're a gaping hole in our understanding of how the most energetic particles in the universe behave. Take the case of pion decay, a process that should be unavoidable. When ultra-high-energy protons collide with photons from the cosmic microwave background, they typically create unstable particles called pions, which almost immediately decay into gamma rays. It's a fundamental prediction of particle physics, one that's been confirmed in Earth-bound accelerators countless times. Out in space, though, the math falls apart. Observations from gamma-ray telescopes like Fermi LT and Hawk reveal far fewer high-energy photons than models predict, as if the universe has quietly switched off a law of physics somewhere between our labs and distant galaxies. The implications ripple through multiple theories. Active galactic nuclei, supermassive black holes powering some of the universe's brightest objects, should be prime suspects for producing both ultra-high-energy cosmic rays and their gamma-ray counterparts. But when researchers match cosmic ray detections with gamma-ray maps, the correlations crumble. Some of the most energetic particles seem to arrive without any accompanying electromagnetic fanfare, like unmarked bullets fired from a gun with no muzzle flash. One radical explanation suggests that magnetic fields might be scrambling the evidence. Gamma rays travel in straight lines, but if their parent cosmic rays get twisted by intergalactic magnetic fields, the two could appear to come from completely different directions, masking their connection. The problem: fields strong enough to create this level of misdirection would leave other, observable imprints on galaxies and galaxy clusters, imprints we haven't found. Then there's the dark matter angle. If some ultra-high-energy cosmic rays come from decaying or colliding dark matter particles, they might produce different byproducts than conventional astrophysical processes, perhaps particles that don't generate the expected gamma-ray signatures. It's an enticing idea, but without direct evidence of dark matter's true nature, it remains a speculative escape hatch rather than a solution. The most unsettling possibility, though, is that we've misunderstood the cosmic rays themselves. What if these particles aren't protons or ion nuclei, but something more exotic, a form of matter that interacts so weakly with photons that it bypasses the usual decay chains entirely? Theorists have floated ideas like strangelets, hypothetical chunks of strange quark matter that could carry immense energy without playing by the standard rules. The missing photons aren't just an observational hiccup, they're a cosmic paradox, forcing us to question whether our models of particle physics hold up at energies far beyond anything we can recreate on Earth. Every time a telescope fails to spot the gamma rays we expect, the universe whispers a challenge. If the rules don't fit the evidence, maybe we're reading the wrong rulebook. Scientists pride themselves on consistency. Measure something once, measure it again, and the numbers should match. But cosmic rays have a way of laughing at our assumptions. Meet the chameleon events, ultra-high-energy particles that seem to change their very nature upon retesting, leaving researchers questioning whether they're glimpsing exotic physics or chasing detector gremlins. It started as a nagging inconsistency at the Pierre Auger Observatory. In 2016, a cosmic ray registered as a heavy ion nucleus, a logical finding given its energy signature. But when scientists recalibrated their instruments and reanalyzed the data months later, the same event suddenly looked like a lightweight proton. At first, they dismissed it as a processing error until it happened again. And again. Soon, similar reports trickled in from other observatories, particles that couldn't seem to decide what they were. Some flipped between helium and carbon, others oscillated between silicon and oxygen. These weren't minor calibration blips, the differences spanned entire swaths of the periodic table, as if the particles were wearing cosmic disguises. The implications rattle the foundations of particle physics. If these shifts reflect real properties rather than instrument noise, we might be seeing evidence of metastable, exotic matter particles that briefly exist in multiple states before settling into a detectable form. Picture a cosmic chameleon cycling through identities mid-flight. An ion nucleus one moment, a proton the next, its quark structure rearranging like a Rubik's Cube tumbling through space. Theoretical models predict such behavior for certain beyond standard model particles, including hypothetical strangelets, clusters of quarks with unusual stability. But if these particles exist, they'd require energies and conditions far beyond anything we've recreated in particle colliders. Detector artifacts offer a more mundane but equally troubling explanation. Ultra-high-energy cosmic rays collide with our atmosphere in chaotic, cascading showers, and reconstructing their original composition from this particle debris is notoriously tricky. Magnetic fields can skew measurements. Overlapping showers might masquerade as single events. even atmospheric humidity has been caught distorting results. The AGASA team ran exhaustive tests, isolating variables from software algorithms to hardware responses. Yet some chameleon events resisted all explanations, their compositional shifts persisting even under rigorous scrutiny. The most unsettling cases come from joint observations where multiple detectors witness the same cosmic ray yet disagree on its identity. In 2019, Japan's telescope array caught a particle that read as nitrogen, while Argentina's AGASA detectors, analyzing the same event hours later, flagged it as neon. With no obvious atmospheric interference or equipment malfunctions, the discrepancy highlighted a terrifying possibility that these particles might somehow evolve en route, shedding or absorbing energy in ways that alter their detectable signatures. Could this be dark matter's fingerprint? Some theorists speculate these morphing particles might be interacting with invisible halos around galaxies, briefly changing states as they pass through clouds of weakly interacting massive particles. Others suggest more radical ideas, like quantum decoherence at macroscopic scales where a single particle's properties remain fundamentally uncertain until measured, not just in lab experiments but across interstellar distances. For now, the chameleon cosmic rays remain in limbo, too consistent to ignore, too bizarre to comfortably explain. They challenge not just our instruments, but our very understanding of how matter behaves at energies we can't replicate. And with each new shape-shifting detection, they whisper the same unsettling question. When a cosmic ray refuses to sit still, who's to say what's real? The Virgo supercluster should be a cosmic graveyard, at least when it comes to ultra-high-energy particle production. Spanning 100 million light-years and housing over 100 galaxy groups, this sprawling neighborhood includes our own Milky Way in its suburban fringes. Unlike the dense, violent cores of distant superclusters, Virgo's galaxies are relatively sedate. No screaming quasars, no colliding giants, just the quiet hum of middle-aged stars. Yet when researchers trace the paths of several ultra-high-energy cosmic rays detected between 2015 and 2021, their trajectories converged here, pointing to galaxies that by all accounts shouldn't be capable of such extreme astrophysical violence. What makes this alignment so perplexing isn't just the mismatch between energy and environment, it's the sheer audacity of the numbers. Take the event nicknamed Virgo's Hammer, a particle detected by the telescope array in 2018 with an energy of 150 exaelectron volts. For context, that's roughly the kinetic energy of a tennis ball served at 100 miles an hour packed into a single subatomic speck. According to conventional models, accelerating particles to these energies requires conditions found only in the most extreme environments. Jets from supermassive black holes spinning at near light speeds, or shockwaves from colliding galaxy clusters. Virgo's galaxies, while numerous, are cosmic retirees compared to these celestial powerhouses. Theories abound, each more speculative than the last. One possibility involves hidden active galactic nuclei, supermassive black holes that aren't currently feeding enough to glow as quasars but might still produce sporadic particle bursts. It's like assuming a dormant volcano can't erupt because it's not spewing lava today. Another idea points to dark accelerators, structures we can't directly observe, like primordial black holes or decaying dark matter filaments threaded through the supercluster. These could theoretically lurk between galaxies, invisible to telescopes but potent enough to occasionally fling particles across the cosmos. Then there's the intergalactic magnetic field wild card. If the supercluster's diffuse plasma is crisscrossed by stronger than expected magnetic fields, these might act like cosmic rails, funneling particles from distant, truly violent sources and making them appear to originate from Virgo. Imagine a bullet ricocheting down a hallway. By the time it hits you, tracing its path backward would point to the wall, not the shooter, the most unsettling possibility. That we're witnessing the aftermath of something ancient, Superclusters aren't static, they're dynamic webs where galaxies jostle and merge over billions of years. A catastrophic event, a black hole merger, a hypernova could have occurred here tens of millions of years ago, its particle blast only now reaching us. Without an ongoing energy source, we'd see no glowing aftermath, just the silent, high-energy shrapnel arriving eons later. Virgo's cosmic rays force a humbling realization: tranquility in space might be an illusion. What looks like a quiet galactic neighborhood could be hiding relics of past violence, or engines of destruction we don't yet know how to see. Until we solve this riddle, every ultra-high-energy particle from this region carries the same unspoken taunt. The universe's loudest explosions might leave the quietest echoes. On February 17, 2019, gravitational wave detectors in Louisiana and Washington state caught something extraordinary: a ripple in spacetime marking the collision of two neutron stars over 4 billion light-years away. Mere hours later, halfway across the globe, the telescope array in Utah recorded an ultra-high-energy cosmic ray slamming into Earth's atmosphere with the force of a major league fastball. At first glance, it should have been just another cosmic coincidence, except when scientists mapped the cosmic ray's trajectory backward, it pointed nowhere near the neutron-star merger. Worse, the timing was off by nearly 6 hours, a gap that at near light speeds might as well be an eternity. This wasn't just a mismatch, it was a paradox, one that's forced physicists to confront the uncomfortable possibility that our universe's most violent events might be talking to each other in ways we don't yet understand. The first clue to this enigma lies in the numbers. Gravitational waves travel at the speed of light, as do cosmic rays in a vacuum. For both signals to originate from the same cataclysm yet arrive hours apart, something would have needed to delay the cosmic ray or accelerate the gravitational wave. Neither option fits known physics. One tantalizing theory suggests the cosmic ray might have been trapped momentarily, perhaps by an intense magnetic field near the merger, before breaking free and racing toward Earth. Picture a surfer caught in a whirlpool before being spat back into the current. The math is speculative, but not impossible if the field was strong enough to stall a particle moving at 99.9999% the speed of light. Then there's the direction problem. The neutron-star collision occurred in the constellation Hydra, while the cosmic ray seemed to originate from a quiet patch of sky near Pegasus, a discrepancy of over 100 degrees. Traditional astronomy says these points shouldn't be connected, but what if spacetime itself acted as a cosmic prism? Some models of quantum gravity predict that ultra-high-energy particles might interact subtly with the fabric of the universe, bending their paths in ways that defy classical geometry. It's as if the particle took a shortcut through a dimension we can't see, emerging from a point that seems unrelated to its true origin. The wildest explanation, though, involves shockwaves in the intergalactic medium. Neutron star mergers don't just emit gravitational waves, they unleash torrents of gamma rays and high-energy particles. If this blast encountered a previously unknown structure, a filament of dark matter, a pocket of warped space-time, it might have redirected some of its energy, like an echo bouncing off a hidden canyon wall. The cosmic ray we detected could have been a shard of that redirected energy, arriving later and from an unexpected angle. What makes the time anomaly event so unnerving isn't just the mismatch, it's the implication that our universe's most explosive moments might leave fingerprints we're only beginning to recognize. Every time a cosmic ray and a gravitational wave arrive in tantalizing near miss, it's a reminder that the cosmos doesn't just operate in straight lines and perfect synchrony. Sometimes the most profound connections are the ones we have to piece together, one fragmented signal at a time. Deep in the cosmic microwave background, the faint afterglow of the Big Bang, there's a patch of sky so bizarre, astronomers call it the cold spot. Stretching nearly 2 billion light-years across, this region is colder than its surroundings by a few millionths of a degree, a tiny but statistically significant anomaly that's puzzled scientists for decades. Some say it's a glitch in the data, others whisper about parallel universes bumping against our own. But here's where it gets even stranger. When researchers mapped the paths of several ultra-high-energy cosmic rays, a handful pointed straight toward this cosmic curiosity. Not toward a galaxy, not toward a black hole, but toward what appears to be a vast, near-empty void. The cold spot isn't just cold, it's suspiciously sparse. Most of the universe's matter clusters into galaxies and galaxy filaments, but this region is eerily understaffed, missing about 20% of the expected galaxies. Voids like this aren't unheard of, but their typical sizes cap out around 100 million light-years. The cold spot dwarfs them all, a cosmic desert so expansive it defies standard models of structure formation. And yet, against all odds, it might be flinging particles at Earth with energies that rival the most violent quasars. How does nothingness become a particle accelerator? One radical theory involves dark energy, the mysterious force accelerating the universe's expansion. If dark energy isn't perfectly uniform, it could create pockets where space-time itself stretches faster than usual, generating shock waves that ripple through the void. These hypothetical dark energy tsunamis might briefly act like cosmic slingshots, hurling stray protons or atomic nuclei to unfathomable speeds. It's a stretch, but not impossible. Simulations show such processes could produce particle energies in the ballpark of what we've detected. Then there's the quantum tunneling hypothesis. In the vacuum of space, particles constantly pop in and out of existence thanks to quantum fluctuations. Normally, they annihilate too quickly to matter, but in a void as vast as the cold spot, some theorists suggest these fleeting particles might have just enough time to tunnel through space-time barriers, emerging with energies that cheat the usual cosmic limits. Think of it like a surfer catching a wave that shouldn't exist, except the wave is woven from the fabric of reality itself. But the most tantalizing clue comes from magnetic fields. Even in voids, the universe isn't truly empty. It's threaded with diffuse plasma and weak magnetic fields. If these fields are more tangled or dynamic than we've assumed, they could act like invisible cosmic pinball machines, bouncing particles back and forth until they're ejected at extreme velocities. The catch: we've never detected fields strong enough to explain this unless the cold spot hides a magnetic relic from the early universe, a fossilized ripple from the Big Bang's first seconds. Every ultra-high-energy cosmic ray tied to this void carries the same unspoken challenge. The universe's quietest corners might be hiding its loudest secrets. And until we peer deeper into this cosmic anomaly, the cold spot will remain both a mystery and a beacon, a reminder that sometimes the most profound questions aren't found in the stars but in the spaces between them. In the frozen depths of Antarctica, where ice cube sensors peer upward through a kilometer of glacial ice, physicists witnessed something extraordinary in 2020. A high-energy neutrino, a ghostly particle that barely interacts with matter, slammed into the ice with pinpoint precision. Mere hours later, thousands of miles away, the Pierre Auger Observatory in Argentina caught an ultra-high-energy cosmic ray streaking through the atmosphere. On their own, these detections would have been routine, but when researchers compared notes, their jaws dropped. Both particles arrived from the same patch of sky, with trajectories suggesting a shared origin. Dubbed the neutrino handshake, this unlikely pairing could be the key to unlocking one of astrophysics' greatest mysteries, where cosmic rays are born. Neutrinos and cosmic rays rarely travel in pairs. Think of them as two strangers passing in the night, one a silent shadow, the other a screaming meteor. Neutrinos zip through planets like they're not even there, rarely leaving a trace. Cosmic rays, by contrast, announce their presence with explosive particle showers. But when both appear simultaneously from the same direction, it's like catching a whisper and a shout from the same cosmic megaphone. The odds of this happening by chance. Less than 1 in 1,000. Either the universe rolled cosmic dice and hit a statistical jackpot, or we're seeing the aftermath of a single cataclysmic event. The prime suspect, a flaring blazar, a supermassive black hole at the heart of a distant galaxy, spewing jets of plasma directly toward Earth. These cosmic blowtorches are among the few engines powerful enough to accelerate particles to such extreme energies. But here's the catch: the suspected blazar, catalogued as TXS 0506 plus 056, lies 4.5 billion light-years away. At that distance, even the most energetic particles should have been slowed to a crawl by interactions with the cosmic microwave background. Yet both the neutrino and cosmic ray arrived with energies that defied these expectations, as if they'd cheated the universe's speed limits. One theory suggests the blazar's jet might have contained dense knots of plasma-localized regions where magnetic fields coiled tighter than a snake poised to strike. If particles got trapped in these magnetic whirlpools, they could have gained energy through multiple passes, like a baseball being fed through a pitching machine again and again until it's launched at impossible speeds. When the knot finally unraveled, it might have ejected both neutrinos and cosmic rays in unison, like a cosmic double-barreled shotgun, but the plot thickens. Neutrinos are typically born alongside gamma rays during particle collisions. When IceCube alerted astronomers to the neutrino detection, telescopes worldwide swiveled toward TXS 0506 plus 056, expecting to see a gamma-ray fireworks display. Instead, they found the blazar in a quiet state, no dramatic flares, no unusual activity. It's as if the universe handed us a signed confession but left the murder weapon nowhere to be found. This disconnect has led some researchers to propose an even wilder scenario, that the neutrino and cosmic ray weren't produced by the blazar directly, but by something in its environment. Picture a blazar's jet plowing into a dense cloud of gas. The resulting shockwave could act as a secondary accelerator, boosting particles to extreme energies without the telltale gamma-ray signature. Others speculate about beam dumps, where high-energy photons from the jet collide with ambient radiation, spawning neutrinos and cosmic rays through cascading interactions. The most tantalizing possibility, though, is that we're seeing the fingerprints of dark matter. If the blazar's jet passed through a clump of invisible particles, their annihilations could have produced both the neutrino and cosmic ray without the usual electromagnetic fanfare. It's a long shot, but not impossible, and it would explain why the blazar itself seemed so calm during the event. For now, the neutrino handshake remains a cosmic cipher, a fleeting moment of coordination between two elusive messengers. But with every new detection, we're learning to listen more carefully to these whispers from the void, because sometimes the universe's deepest secrets aren't just hidden in what we observe, but in how its pieces unexpectedly align. At the smallest scales, imaginable trillions of times tinier than an atom, the fabric of spacetime might not be smooth but foamy. Quantum gravity theories predict that at the so-called Planck scale, space itself could be pixelated, a seething quantum froth where reality flickers between existence and oblivion. It's a realm far beyond our direct observation. But what if ultra-high-energy cosmic rays are leaving fingerprints of this hidden granularity as they streak across the universe? Consider this: when a cosmic ray travels billions of light-years, every bump and tremor in spacetime's theoretical foam should leave a mark, like a bullet passing through a turbulent storm. These minute interactions would subtly alter the particle's energy, imprinting a signature so faint it's nearly invisible. Yet in 2012, researchers analyzing data from the Pierre Auger Observatory spotted something peculiar. A handful of ultra-high-energy cosmic rays arrived with energy spectra that didn't quite match standard models. The deviations were minuscule, less than a fraction of a percent, but clustered in a pattern that hinted at interference from something beyond known physics. One explanation: quantum gravity's granularity. If spacetime is indeed frothy at Planck scales, high-energy particles moving near light speed would interact with this foam, scattering ever so slightly in ways that depend on their energy. Imagine running your hand through water versus thick syrup. The resistance changes with speed and texture. For cosmic rays, this could manifest as energy-dependent delays or dispersions, a phenomenon dubbed vacuum dispersion. The higher the energy, the stronger the effect. It's as if the universe's tiniest structures are whispering to us through these particle anomalies, but the plot thickens. Not all quantum gravity models predict the same signatures. Some theories, like loop quantum gravity, suggest spacetime's granularity would cause energy losses that grow with distance traveled. Others, like string theory-inspired models, propose frequency-dependent speed variations. The cosmic rays we've detected so far offer tantalizing but contradictory clues. A few seem to support dispersion effects, others show no deviation at all. This inconsistency has split physicists into two camps: those who believe we're glimpsing the first hints of quantum gravity, and those who argue the anomalies are mere statistical noise or unaccounted for astrophysical processes. The smoking gun might lie in neutrinos. Unlike charged cosmic rays, which twist and turn in magnetic fields, neutrinos fly straight, making them ideal probes of spacetime structure. If both neutrinos and cosmic rays from the same distant source show synchronized energy shifts, it could rule out magnetic interference and point squarely at quantum gravity. The challenge, catching these ultra-high-energy neutrino counterparts, is like fishing for ghosts in a hurricane. They're vanishingly rare, and current detectors lack the precision to match them definitively with cosmic ray events. What makes this search so electrifying isn't just the potential discovery, it's the sheer audacity of the method. By treating cosmic rays as cosmic microscopes, we're probing scales a billion times smaller than the nucleus of an atom, using the universe itself as our laboratory. And if the whispers in the data prove real, we might finally answer a question that's haunted physics for a century. What does spacetime look like when you zoom in past the limits of imagination? For now, the quantum gravity clue remains elusive, etched into the faintest wrinkles of particle data. But with next-generation observatories like the probe of extreme multi-messenger astrophysics preparing to launch, we're on the verge of either cracking spacetime's smallest secrets or learning just how craftily the universe guards them. Physics has a graveyard of abandoned theories, ideas once elegant but ultimately undone by evidence. But every so often, something claws its way back from the dead. That's exactly what's happening with ultra-high-energy cosmic rays. As researchers dust off decades-old concepts like topological defects and superconducting cosmic strings to explain particles that refuse to fit modern frameworks. These aren't just tweaks to existing models, they're full-blown resurrections of ideas once deemed too speculative to take seriously. And the reason is simple. When the universe keeps hurling impossible particles at your detectors, you start digging through the archives for answers. Take topological defects, a relic from the early universe's chaotic infancy. Picture the cosmos moments after the Big Bang, cooling from a seething plasma into the structured reality we know. Like ice forming on a pond, this phase transition shouldn't have been perfectly smooth. Cracks and seams might have formed in spacetime itself. One-dimensional cosmic strings, two-dimensional walls, or even zero-dimensional point-like defects. These scars in the universe's fabric were long considered mathematical curiosities, until ultra-high-energy cosmic rays started showing up with energies no known process could explain. Now, these defects are back on the table as potential particle accelerators. A snapping cosmic string, for instance, could release enough energy in a single burst to fling particles across the universe with the force of 1 billion supernovas. It's as if we've discovered bullets with no gunner and realized the shooter might be the fabric of reality itself. Then there's superconducting cosmic strings, an even wilder twist. Theorized in the 1980s, these aren't just flaws in space-time, they're flaws carrying electric currents, cosmic-scale power lines humming with energy. If one such string threaded through our galaxy, it could act like a natural particle collider, accelerating protons or heavier nuclei to velocities that defy conventional limits. The math is daunting, but the beauty of this zombie theory lies in its testability. Unlike dark matter or extra dimensions, superconducting strings should leave subtle imprints on the cosmic microwave background or warp the light of distant quasars. So far, searches have come up empty, but with each new ultra-high-energy detection that resists explanation, physicists are giving these relics a second look. What makes this theoretical resurrection so unsettling isn't just the science, it's the philosophical whiplash. For years, the mantra has been new physics, chasing exotic particles or undiscovered dimensions to explain cosmic anomalies. But the zombie model crisis flips the script. Maybe the answers aren't ahead of us, but behind, buried in equations scribbled on chalkboards half a century ago. And that's the real lesson here. When the universe breaks its own rules, sometimes the most radical solution isn't to invent new ones, but to revisit the ones we'd prematurely buried. After all, in a cosmos where particles regularly outpace theory, there's no shame in letting the dead speak. Dark matter might be the universe's most reluctant celebrity. Everyone knows it's there, but no one's ever seen it directly. Yet if certain theories are right, this invisible cosmic scaffolding could be quietly crumbling, sending ultra-high-energy cosmic rays screaming toward Earth like cosmic distress signals. The idea isn't as far-fetched as it sounds. If dark matter consists of weakly interacting massive particles (WIMP), their eventual decay or mutual annihilation could unleash bursts of energy capable of producing the most extreme cosmic rays we detect. Picture a ghostly fireworks show, invisible to telescopes but leaving behind traces in the form of particles so energetic they defy conventional astrophysics. The math is compelling. WIMP, if they exist, would clump in the halos around galaxies, including our own Milky Way. Over billions of years, these particles might occasionally collide or decay, converting their mass into pure energy through Einstein's famous equation. The resulting explosions, while invisible to light-based telescopes, could theoretically spit out protons or atomic nuclei with energies exceeding 100 exa-electron volts. It's a tidy explanation for cosmic rays that seem to come from nowhere, their paths untraceable to any visible source. But here's the catch. If dark matter is decaying uniformly across the galaxy, why don't we see an even distribution of these events in the sky? Instead, ultra-high-energy cosmic rays arrive in clumps and voids, like breadcrumbs scattered randomly rather than evenly poured. Ambiguity piles up when you consider competing signals. If WIMP were truly behind these cosmic rays, their decay should also produce gamma rays and neutrinos in predictable ratios. Yet observatories like Fermi and IceCube often come up empty when searching for these accompanying signatures near cosmic ray hotspots. It's like hearing a gunshot but finding no smoke or shell casing, suggesting either dark matter behaves in ways we haven't modeled, or something else is mimicking its fingerprints. The plot thickens with alternative dark matter candidates. Actions, sterile neutrinos, or even primordial black holes could decay or collide differently than WIMP, producing cosmic rays without the expected secondary particles. Some theories propose hidden sectors of dark matter, shadowy families of particles that interact through forces we've yet to discover. These could decay into exotic states that manifest only as ultra-high-energy cosmic rays, bypassing other detection methods entirely. It's a tantalizing loophole, but one that leaves physicists in a bind. How do you test a theory that deliberately avoids leaving evidence? For now, the dark matter decay hypothesis remains in limbo, neither proven nor disproven, but lingering as a ghostly possibility. Every unexplained cosmic ray is a reminder that the universe's biggest mysteries might not be written in the stars, but in the invisible ink of particles we're still learning to read. And until we catch dark matter in the act, these ultra-high-energy enigmas will keep us guessing, one impossible particle at a time. Imagine a bubble universe floating just beyond the edge of our own, a realm where gravity is stronger, light travels slower, or perhaps atoms never formed at all. Now picture that universe brushing against ours, its border thinning just enough to let something slip through. This isn't science fiction. It's one of the boldest explanations for ultra-high-energy cosmic rays that refuse to play by our universe's rules. Dubbed the multiversal intruder hypothesis, this idea suggests that some UHECR might not be products of black holes or dark matter, but refugees from realities with entirely different physics. The math behind this theory is as elegant as it is unsettling. In certain multiverse models, parallel universes could exist with higher energy scales, places where the fundamental constants that govern particle interactions are dialed up to extremes. In such a reality, particles might naturally reach energies that would be impossible here, like fish from deeper ocean trenches surviving pressures that would crush shallow water species. If a cosmic accident, a quantum fluctuation, a collision between universes briefly thinned the barrier between worlds, these foreign particles could tunnel into our cosmos, arriving with energies that leave our detectors blinking in disbelief. Critics are quick to point out the obvious. This sounds like cheating. Invoking other universes to explain anomalies risks becoming a theory of anything, untestable and vague. But proponents counter with a tantalizing clue: the GZK cutoff's occasional violations. If UHECR are coming from beyond our universe, they wouldn't interact with our cosmic microwave background the way homegrown particles do, neatly sidestepping the energy loss that should slow them down. It's like finding a marathon runner who isn't sweating because they trained on a planet with no atmosphere. The smoking gun might lie in particle composition. If a multiversal cosmic ray arrived made of matter not found in our universe, exotic quark configurations or particles carrying unfamiliar quantum numbers, it would stand out like a fingerprint at a crime scene. Some researchers are sifting through old data from the Pierre Auger Observatory, hunting for anomalies in air shower patterns that could hint at alien physics. Others are running simulations to predict how particles from a universe with, say, stronger nuclear forces might fragment upon entering ours. Yet the most compelling evidence might be absence itself. The most extreme UHECR often point back to cosmic voids, regions with no visible accelerators. If these aren't just gaps in our maps but thin spots in the fabric between realities, their emptiness suddenly makes poetic sense. Perhaps the great nothing isn't empty at all, but a window. Of course, extraordinary claims require extraordinary evidence, and right now, the multiverse remains firmly in the realm of what if. But history has shown us that today's heresy often becomes tomorrow's textbook. Whether these cosmic rays are messengers from other dimensions or just another puzzle in our own, their very existence reminds us that the universe or multiverse still holds cards it hasn't shown us. And that's the real magic, not the answers we have, but the questions we've yet to ask. Scientists have spent over a century chasing cosmic rays, setting up detectors in deserts, burying them under ice, even floating them on balloons, but the answers keep slipping through our fingers. Now, a new generation of observatories is gearing up to rewrite the rules of the game. Imagine telescopes that don't just peer at the sky from Earth's surface, but hover in orbit, scanning the atmosphere for the faint ultraviolet glow left by ultra-high-energy cosmic rays. That's POMA, the probe of extreme multi-messenger astrophysics, a pair of satellites designed to work in tandem, covering the entire night side of Earth with a sensitivity that dwarfs anything we've built before. Unlike ground-based arrays that wait for particles to hit them, POMA flips the script. Its cameras will lock onto the streaks of nitrogen fluorescence produced when cosmic rays rip through the upper atmosphere, glowing trails too faint for most telescopes to see, but visible from space with startling clarity. By orbiting at over 500 kilometers up, these satellites avoid atmospheric distortion entirely, capturing particle showers with a precision that could finally pinpoint cosmic accelerators hidden in the void. Even more groundbreaking, POMA's ability to spot ultra-high-energy neutrinos. If these ghostly particles accompany cosmic rays from their violent birthplaces, as theory predicts, this dual detection could crack open the case like nothing before. Meanwhile, on the ground, an even more audacious project is taking shape. The giant radio array for neutrino detection GRAND plans to blanket over 200,000 square kilometers with simple radio antennas from mountainous regions to arid plains. These won't look like traditional telescopes. Think of them as cosmic lightning rods, tuned to catch the nanosecond radio pulses emitted when ultra-high-energy particles collide with Earth's magnetic field. GRAND's sheer scale lets it act as both a cosmic ray detector and a neutrino hunter, stitching together a global net to catch particles that current setups miss. What makes these projects revolutionary isn't just their technology, it's their strategy. For decades, we've treated cosmic rays, neutrinos, and gamma rays as separate puzzles. POMA and GRAND blur those lines, searching for correlations between these messengers like detectives cross-referencing alibis. If a neutrino arrives from the same patch of sky as a cosmic ray, or if a gamma ray burst coincides with a particle detection, these observatories will spot the connection in real time. It's a shift from chasing single particles to reconstructing entire cosmic crime scenes. Yet the boldest ideas aren't just about bigger detectors, they're about smarter ones. Machine learning algorithms now sift through petabytes of data, flagging anomalies human eyes might miss. Some theorists even propose attaching detectors to asteroids, turning the solar system into a natural particle collider. Others dream of lunar observatories, where the moon's lack of atmosphere and radio noise could reveal cosmic rays with pristine clarity. The questions driving these missions read like a cosmic wish list. Are topological defects real? Does dark matter decay? Is spacetime foam leaving fingerprints on ultra-high-energy particles? With each new detection, we're not just collecting data, we're interrogating the universe itself. And if history's any guide, the answers won't just solve old mysteries. They'll reveal ones we haven't even thought to ask. From the oh my god particles' earth-shattering energy to the eerie precision of the telescope array hotspot, these 30 cosmic anomalies aren't just outliers, they're rebellion in particle form, each one a defiant scratch across the blackboard of modern astrophysics. Think of them as cosmic conspiracy theorists, whispering in numbers that don't add up, pointing to voids where accelerators should be, and arriving with energies that make black holes look tame. The sheer audacity of their existence forces us to confront an uncomfortable truth. Our maps of the universe might be missing entire continents of physics. Take the collective contradictions, how particles like the fly's eye event smash through the GZK cutoff as if it were tissue paper, while the iron nuclei paradox laughs at the fragility of matter over cosmic distances. Or consider the ghostly coordination between neutrinos and cosmic rays in the neutrino handshake, a partnership that shouldn't survive a 4 billion light-year journey. And what about the void ray, barreling out of the Boötes desert like a bullet fired from an empty gun? Together, they form a mosaic of mysteries where every piece undermines a different assumption about dark matter, magnetic fields, even the fabric of spacetime itself. What's breathtaking isn't just the individual anomalies, but the patterns they hint at. Why do so many ultra-high-energy cosmic rays cluster in ways that defy probability? Why do some arrive from regions devoid of known accelerators, while others, like the lone galactic intruder, seem to hail from our own galactic backyard, where nothing should be powerful enough to create them? It's as if the universe has built a shadow network of particle factories, invisible to our telescopes but undeniable in their output. And then there's the philosophical whiplash. The resurrection of zombie theories, cosmic strings, topological defects, multiversal leakage proves how desperate we've become for answers. These ideas weren't pulled from thin air. They're the last cards left in the deck after all others failed. When particles arrive with energies that dwarf the Large Hadron Collider's output, or when they point to voids colder and emptier than any natural accelerator should allow, you start questioning whether natural even applies anymore. But here's the beautiful part. Every unsolved cosmic ray is an invitation. With Poma orbital eyes and grand continent-spanning antennas, we're not just building better detectors, we're setting traps for the impossible. The next oh my god particle might carry the signature of quantum gravity. The next void ray could reveal dark matter's decay. Or maybe, just maybe, the next detection will be so bizarre it'll rewrite the questions entirely. So keep watching the skies, not just for answers, but for the next great cosmic curveball. Because if there's one thing these 30 mysteries teach us, it's that the universe thrives on defiance. And the day we stop being surprised is the day we stop discovering.